Okay. So, does anybody remember anything about continuity or what a continuous function is?
What is that again? Wait, what?
A continuous function? Does anybody know anything about a continuous function? Functions that are continuous?
No.
All right, let me give you a quick definition in my words.
I don't want to. I give up. Like, who hasn't even talked to you yet? I'm so interested. What's that chapter called?
2.4, continuity.
2.4?
5.
I don't know why I'm not drunk. Like, somebody use function like
Continuity.
I actually don't know what I can do.
Continuity.
All right, so did you write this down? A continuous function is a function that you can draw without lifting your pencil. Okay, so that means that there are no vertical asymptotes, there's no jumps, like a piecewise function, and there's no, what else could we have? No steps, sure.
Why is it when I try and take a picture of it?
And no holes, good.
Rainbows everywhere. No joke, it's weird.
Maybe you should put your phone down so we can learn. Then I don't have to teach it 10 times.
I took a picture of it.
Of the notes?
Yeah.
You have your laptop in front of you?
What?
It's right here in the laptop.
You see?
I'm saying that
I'm
it's...
not open to that, sorry. Well, why aren't you? What do you have to
All right, so anyways, a function that I can draw without lifting my pencil. Can someone give me an example of a continuous function that you've known? Y equals x, perfect. Okay, a straight line is continuous. Okay, parabolas are continuous. John Travolta's, continuous. Can you give me an example that is not continuous? Piecewise functions. Okay, so not continuous would be a piecewise, so something like this, right? Or a step function, okay?
Where this multi?
Yes.
We started, my mom like brought up John Travolta and like she was talking about him and I was really confused.
Oh.
I was like, why are you talking about a graph? And she's like, what the hell?
All right, so let me tell you that there are two types of discontinuity. Two types of discontinuity. Discontinuity. Okay, the first type is called removable discontinuity. Okay, removable discontinuity is when you have a hole in the graph. Okay, so hopefully that makes sense to your brain, because if I was to remove that one single hole, it would otherwise look continuous.
Did you just say that? Holes don't belong?
What?
No holes.
No holes.
That's what it
Right.
says.
Discontinuity, so places where it is not continuous. Discontinuity means not continuous. Okay, so we got removable discontinuity. The other kind is non-removable. Okay, so non-removable discontinuity is when the function like visually splits apart. Okay, so that's going to happen when you have vertical asymptotes or jumps or steps, anything like that. Okay, so visual discontinuity. Okay, ready for an example? I'll take that as a yes.
Discontinuity or continuous?
Which one is, okay, so let me explain then. Okay, so let's say the function was 2 over x minus 5. So what they're going to say is state where the function is continuous. And then also identify your types of discontinuity. Discontinuity. Okay, so the first thing that we're going to do is decide where we have our discontinuities. Okay, so I'm looking for vertical asymptotes, holes, jumps in the graph. Okay, on a rational function like this, rational function meaning I have a fraction, an x in the bottom, I should be concerned about values that make the denominator 0. Because the math god said, thou shalt not divide by 0, and that creates discontinuity in functions. Okay, so tell me what I have here. What kind of discontinuity do I have? Okay, everybody okay with the fact that I have a vertical asymptote at the value of x equals 5?
Yes.
Okay.
But you can't have that.
Exactly. That's exactly what we're
How
saying.
did you get that?
So what value makes the denominator 0? 5. Okay, so as long as it doesn't cancel out with the top, then I have a vertical. I don't choose to put 5 there. It's the value that makes the denominator 0. I can't put a 5 in there or I get an undefined value. Right?
So you can make any graph. I can see.
Well, if they give you a function, I mean, you can create a function with any vertical asymptote. But if I give you a function, you can't just make a vertical asymptote wherever you want. Okay, so we have a vertical asymptote at 5. So what I'm going to say is what kind of discontinuity is a vertical asymptote? Non-removable. So I'm going to say we have a non-removable discontinuity at x equals 5. Okay? So now what I'm going to do is state where the function is continuous. So basically everywhere else the function is continuous. So where is this function continuous? From what to what? Using x values. So we start from negative infinity. So negative infinity 2 to 5. And do I include 5? No, because that's where it's not continuous. And then from 5 to infinity. So basically every single value except for 5. Okay, let's do another one. Same scenario here. Let me see if I can do, let's see.
Can I see the graph? Because I was trying to do this.
What would it look like?
Yeah.
It would just look like, so I'd have negative 5. Vertical asymptote. It's an hourglass. It would look like this. Oh, 5. My bad. Sorry, wrong direction. But shift that sucker to the right 10 units. Positive 5. Good call. Does that make sense, though? See how there's two like continuous pieces, and they split apart at that vertical asymptote from the denominator of the function.
So if there's like
So
any
there's
way
two
to
right
get
there,
bottom
then
can
it's
equal
the
0,
vertical asymptotes of 2.
No, the denominator.
And there's negative 2.
Okay, let's do another one. So let's say we have x minus 3 over x plus 2 and x minus 3. Okay, so if this was my function, what do you notice right away?
I'm taking away the x minus.
Okay, so things can cancel. Now tell me what happens when things cancel. There is a hole in the graph. Okay, so if these things can cancel, that tells me that I have a hole. Okay, what is the x value that makes that quantity 0? 3. So I have a hole at x equals 3. Okay, so now if I was going to cancel out those two quantities, what value now will make the denominator 0? -2. So what's happening at -2? We have a vertical asymptote. So we have a vertical asymptote at -2. Okay, so tell me, what are my types of discontinuity?
You have both types.
Okay, where? So, good, removable at x equals 3. And so the other kind is non-removable. Oops, removable at x equals -2. Okay?
What do you mean by removal?
The idea of removable is like, so think of this for a second. Let's just pretend that our function was a straight line with one little hole in it. Okay, so there was a little hole. So if I was going to remove that one little point, do you see what I mean by that? It would then look continuous.
So you can't remove an asymptote?
Well, yeah, I mean, it looks way different. Like a removable looks continuous. Like if I graphed that function in a calculator, that one right there, it would look continuous. I wouldn't be able to see the hole. But a vertical asymptote, a non-removable discontinuity, I can see in the graph. Like it splits apart. It's very obvious. Okay, so now tell me where this function is continuous. Between what values? So -infinity to -2.
Oh wow, this is
Good.
-3 to +.
3 to infinity. There you go.
It's like I'm going to do this simple.
Yeah, it never is.
I'm looking at the homework. It is that simple. Okay. So let's say we have a piecewise function. Let's do one like that. Okay. So the other places where you see discontinuities are piecewise functions, rational equations. Often they'll ask you about continuity with square root functions. We can do one of those too. Let's do a piecewise function. Let's say x squared for values that are less than 0, and we'll do x plus 1 for values greater than or equal to 0. Okay. So if I have a piecewise function, the first thing I'm going to do is I'm going to look at each of the pieces individually and see if each of those pieces has any kind of discontinuity. Okay, if I was going to look at just x squared, is there any value that x cannot be? No. It can still be 0. 0 squared is 0. That's a number. That's okay. Can't divide by 0. That's different. Okay, so x squared is continuous. I don't have any issues with that. What about my bottom piece, x plus 1? -1, but -1 plus 1 is 0. That's a number. We're not dividing by 0. See the difference? You can have 0, not divide by 0. So we don't have any x's in the denominator. Okay, so each of those two pieces is continuous. So the question is, do these two functions come together when they have their intervals connect? Okay, so if I was going to draw this, x squared for the value is less than 0, I'm going to stop drawing when the x value is 0. 0. Okay, so if I plug in 0, what is its corresponding y value? If I plug in 0, what do you get? 0. Okay, so now I want to see if this is going to be the same value, and they're going to come together, they're going to join. So if I plug in 0 into this piece, what do I get? 1. So are these two pieces coming together at the same place? No. So there's a jump in the graph. If I was going to graph this, I could visually see what is happening. It would look like this. I'd go, wow, that was a really bad parabola. So I have my left arm on my parabola, and then it would go like this. So I'd have a hole here. It would look like that. Okay, so tell me, if I have a jump in the graph, what kind of discontinuity is that? Non-removable. It's a physical, I can see it. So it's a non-removable. What is the x value it happens at? Good, so x equals 0. Okay, so now we can tell where this function is continuous. It is continuous from infinity to 0, and 0 to infinity.
So how do you know whether to include 0?
You never include any place where it breaks. You don't include it. Okay. Let's do a quick square root function just to kind of explain this whole idea. Let's say we have a square root of x plus 1. Okay. The thing that we worry about with square roots is that you can't take the square root of what kind of numbers? Negative numbers. So those are imaginary, so we can't work with those. So when you're working with square roots, we have to be careful about what values we can plug into x. Okay, so if we can only take the square root of positive numbers, what I can do is I can take the inside of that square root and set it greater than or equal to 0, basically stating that has to be greater than or a positive number, and then I know which values of x that can only exist. So if I solve that inequality, what do we get? So x has to be greater than or equal to -1. Okay, so what is my continuity? I don't have any discontinuity. There's no places where the function is undefined, but I have a restricted continuous piece. Where is this function continuous from? Good, from -1 to infinity. And I include -1, right? Because I can take the square root of 0. Okay, so just so you can see a visual, this graph, that square root, remember, is the top half of a parabola, goes up and to the right. So I can see it just doesn't even exist on that left side. So it only is from -1 to infinity. Is that starting to click? Okay.
What if it's like square root of x plus 3, which is the
The square root of x plus 3? So if you just take the x plus 3, set it greater than or equal to 0.
so then it would just be x greater than -3.
Right.
So
Yeah.
you can't have -2 and -1.
Greater than, you can have -2 and -1 because you have -2 plus 3, right? Which would be positive 1. That would be okay. Okay, that's it.